if you stay reasonably close. All right, well, I think we'll get started. Thank you, everybody, for joining us on this Wednesday seminar. It's my great pleasure to introduce Professor Dan Westervelt from Lamont-Doherty Earth Observatory at Columbia University to visit us today. Dan is an expert in climate change, air quality, has done a lot of amazing work on modeling the aerosol interactions with climate and air quality. And also, as you can see in the title, and as you hear from the talk, I mean, for people working in the air pollution spaces, and I think environmental in general, everybody talks about there's a huge data gap and the gap in our understanding of global south. And that, in my opinion, that has really done some tremendous pioneering work understanding air quality issues in Africa. So we're really excited to have you here. Thank you.
Thanks. All right. Well, thanks everybody for coming, and thanks for inviting me. It's great to be here. It's my first time on this campus. So yeah, as Minghao said, I'll be talking about kind of two maybe disparate areas of my research, where one of them is focused on aerosol impacts on climate, and one of them is more focused on aerosol impacts on air quality and public health and things like that. So hopefully it's not too much of a whiplash going back and forth to these different topics, but I guess we'll see. And so, yeah, I'm a research professor at Lamont-Doherty Earth Observatory, which is at Columbia University. I first just wanted to put up a special shout out to my group members. So a lot of this work, we're gonna talk about a lot of different of my projects. So almost everybody on this list is gonna be have contributed to some of this work. And you can, if you want to know more about our stuff and who we are, you can go to our website there, aerosol.ldeo.columbia.edu. So the outline of today's talk, kind of hinted at this a minute ago, but so part one is going to be kind of about the climate responses to regional aerosol emission changes. So this is largely going to be a modeling exercise. We use large-scale Earth system models, sort of the IPCC class models, to look at how rapidly changing emissions in different parts of the world, which are often going in different directions based on economies, development state, how those changes impact precipitation, temperature, air quality, et cetera. And then I'm going to introduce sort of a new project that is going on as we speak to address that exact issue. It's called the Regional Aerosol Model Intercomparison Project, or RAMIP. And then part two, we're going to be shifting gears a little bit and talking about sort of getting more air pollution data, air quality data in the global south using a variety of novel measurement techniques. So everything from cheap ground-based sensors to remote sensing to more research-grade methodology, the stuff that you kind of see in labs. So we'll kind of cover all of that. And we'll talk a lot about source attribution as well, as that's one sort of application for this data collection process, is to collect data that's actionable, that you could say like, okay, these are the polluting sources, you know, they're representing X% of the aerosol in this city, so that you can give that information to policymakers, decision makers, and that they're able to act on it. So actionable data. So we'll kick off right here with part one. So the impact of aerosols on climate. The way that aerosols impact climate, just a little bit of background. You have the direct effects. So this is sort of the interaction of aerosols with incoming solar radiation. So you have absorbing and scattering. Generally, these aerosols are more scattering than absorbing, although it really depends on the species of the chemical composition of the aerosols. But if you kind of sum everything up and take the net, you get more of a surface cooling or a scattering effect. So that's the temperature. What about the precipitation? So from the direct effects, the scattering or the absorption of that incoming solar radiation also means that there's reduced solar radiation hitting the surface, and therefore you get reduced sort of vertical motion of air, reduced evaporation, reduced convection, and therefore weakening rainfall, weakening precipitation. So aerosols can impact the precipitation that way as well. And that's sort of demonstrated here on the left. On the right is sort of demonstrating what's the aerosol indirect effects. And so this is about not how aerosols directly interact with the climate system, or sorry, with the solar radiation, but how they instead modulate cloud properties. And so there's kind of, a schematic here that shows that when you have more aerosols, so like a polluted atmosphere, you get a higher cloud droplet number concentration, a smaller average cloud droplet size or effective radius, higher cloud albedo, decreased precipitation. I put a question mark after that because it's really hard to summarize this in just one sentence. It's very heterogeneous and it's not really fully fleshed out yet. There's still a lot of uncertainties in that. But these are sort of the big picture things. And so when you take all this together, I like to think of it more as what's going to happen when aerosols decrease, because really that's the way that the world is going. Due to the strong impact of air pollution on people's health, about 8 million people die every year due to breathing in bad air quality, essentially. The trend is mostly towards reduction in aerosols. And so when you reduce those aerosols, you're kind of removing that cooling effect, and therefore you get mostly temperature increases when you remove aerosols. So aerosols have kind of a very, as I mentioned earlier, heterogeneous nature. So if you look at this first plot here, this is showing the aerosol optical depth in 5 years period, 2016 to 2021. And there's, you can see kind of some trends here where we have high levels in South Asia, over India and East Asia, high levels over West Africa and Central Africa, and then kind of smaller amounts, over North America and Western Europe. And this is sort of a reflection of the, cleanup that's gone on, the Clean Air Act and other policies that have improved the air quality. They've also reduced the total column number of aerosols. So you have this kind of strong, decreasing trend going on in some of the North America and Europe, but then in other places you might have some increases, especially in recent times, in places like India and many countries in Africa. So overall, things are kind of changing in different directions, and there's a real heterogeneous nature of the emissions. And so a question is going to be, how does that impact, climate? So aerosols, impact regional climate significantly, I would say. They strongly impact extreme events. So this plot is showing the extreme precipitation, so 5-day maximum precipitation. And so you can see here, this is, based on some recent aerosol changes. You can see that there's some decreases. We see precipitation decreases over parts of West Africa here, but in other parts, not too far away, we see increases. Same thing in East Asia. You have, I would say, or South and East Asia, you have mostly increases in precipitation due to these recent aerosol trends. But of course, there's a few pockets of decreases as well. And so there's this highly impactful kind of local effect where you have aerosols that are emitted in South and East Asia impacting precipitation and temperature in South and East Asia, but you also have sort of this remote effect. So aerosol emissions also have strong remote influences via teleconnections, and there's a few of them shown here. Things like aerosols in the northern hemisphere impacting precipitation in different monsoon systems. That's a commonly understood thing. So it's really kind of not just about what's emitted locally, but also what emission changes are happening, far field from the local emissions.
In that map you had an upper left to the previous one.
Right here?
Yeah, is that total or anthro?
This is total, so it would include things like biomass burning and stuff, and that's probably why, and dust as well. Yeah.
Thank you.
So yeah, so I kind of hinted at this a little bit, but this is just showing, black carbon emissions globally, and SO2 emissions globally. So SO2 is a precursor to sulfate aerosol. And if you look at the historical period, globally totaled black carbon and SO2 kind of strongly increasing from 1950 up to, maybe in the case of black carbon, still increasing. In the case of SO2, it sort of peaked in like the late 1980s or early 1980s. That's kind of when Clean Air Acts and stuff came aboard. But for either species, these historical projections, which are done by the shared socioeconomic pathways, have, projected mostly decreases globally averaged. But the globally averaged picture is not quite the whole story. And that's what this other map on the right is showing, where we have the difference in AOD between a 3-year period, 2015 to 2018, and another 3-year period, 2010 to 2013. So pretty short time period, but sort of later in the 2010s decade versus early. And in that period, we had large decreases in aerosols over China owing to their cleanup, their improved air quality policy. But at that same time period, you can see increases over India. So things are kind of changing rapidly and in different directions. And so we have this dipole pattern here that we see. But a big question from this that we're going to talk about in the first half of this talk is, what is the impact of these rapidly changing, often in opposite directions, aerosol emissions on climate? So we started looking at this about 10 years ago, and I'll go through some of what we did, but we basically used a series of Earth system models. The model that is built by NOAA, the GFDL, Geophysical Fluid Dynamics Lab, we used that model. We used the Community Earth System model, which is developed by the National Center for Atmospheric Research. And then we also used the NASA Goddard Institute for Space Studies model, which is run actually in New York City at NASA GIS. And what we did is we did these kind of idealized simulations where we said, what if we just shut off abruptly all of the anthropogenic SO2 emissions in a certain region? So what if we shut off all of the anthropogenic SO2 in US? What would be the influence on global climate, global and regional climate? And then kind of repeat that individually for different regions. And not just sulfur dioxide, but also black carbon and organic aerosol as well. So we did that, and this is just some details about our simulation setup. So we had to run very long simulations so that we can separate out the internal variability in the climate system from the force signal from these relatively small changes. All right, so this is not like a doubling of CO2 or something like that, which is a pretty big hammer to hit on the climate system, or a quadrupling of CO2. People do those kind of experiments. This is sort of, what if we just change one type of aerosol or aerosol precursor in one region at a time? So you have to, have very long simulations in order to get signal above the noise and statistical significance. This is a list of the simulations that we did. So there were a total of these 34 kind of perturbation simulations, and we compared these perturbation simulations with a control experiment where everything else was status quo. Aerosols at their 2005 levels. We didn't touch the greenhouse gases or anything like that. All we did was perturb one of these various things at a time. Like if we reduced, zeroed out the SO2 over the US, see what that does, zero out the BC over the US, and then it kind of goes for all these different continents. So there was a lot of different simulations. And this is kind of what we get. So if we look at, this is the spatial pattern of the extreme temperature response to SO2 perturbations. And so what I'm showing here is the perturbation minus the control. So what it represents is sort of the removal of these emissions. Again, just anthropogenic only here. So this would be in the upper row. We have the extreme temperature values in response to removing out the 0 US SO2, and each column is a different model. So we try to use multiple models to assess robustness. Use one model, you might be subject to some of the quirks in that model. You might not feel like it's a robust result. And so it's really good to have multiple models. So that's what we did. And so this first column, shows you this first row shows you the three models results for extreme temperature. This is TXX. So for those that are not familiar with the climate metrics, TXX is the hottest high temperature of the year. Okay, so basically what we're saying here is in a given year, what's the highest high? And we're finding that in response to the removal of this US SO2, which by the way is not really that different from what US SO2 has undergone in the last 50 years. It's not completely zero, but it's pretty close. But what we find is that the highest
This is from the coupled model? Or
yes,
coupled.
fully
And-
coupled air system model.
And the full thing is like a fixed, not evolving with time.
Right. Yes.
Okay.
Yeah. So what you see is that the extreme temperatures increase by about at least 1 degree Celsius over the eastern US in response to US SO2. But there's also some far field changes that we see in Europe. The models kind of largely agree that there's mostly warming. And then kind of a similar story for the European SO2. We see mostly the largest effects always typically occur, I shouldn't say always, but mostly occur local to the emissions, but there still are statistically significant impacts in temperature that happen in different continents. So that's the extremes. The mean temperatures also increase. If you were wondering, we get kind of up to about 0.2 degrees Celsius global mean increase when we reduce these aerosols or these aerosol precursors. And one thing that's kind of interesting is that we get about 1 degree warming in the Arctic. All right, so there's a lot of Arctic amplification going on, and that sort of shows you again that there's these, there's not many aerosol emissions directly in the Arctic. Not many people are living there, so there's not a lot of change. Yeah, question.
Yeah, I was just curious, is this temperature? or
This is surface
air temperature?
surface temperature. Yeah, yeah. Thanks.
And just say, what are the two cases that you're doing the difference between?
Yeah, so in one case, we are zeroing out anthropogenic SO2 over a certain region. The other
From what base year to what?
from 2005. Yeah,
2005. So,
yeah.
so already by 2005, it's way down.
Right, yeah, but it still results in about, I think, 20 teragrams sulfur per year is the perturbation. So it's still pretty large, but yeah, it was decreasing already by 2005. Sure.
Thank you.
So another thing that we looked at was sort of the impact on precipitation. And so what I'm showing here is two different models. So I'm just showing the CESM and the GFDL model. And on the left is the temperature change. So similar to what we saw, this is mean temperature for a certain season, and a different season here for GFDL. But one thing that you see is, I was talking about earlier, this huge amount of warming in the Arctic. So we're removing US SO2 in this time of year, and most of the warming happens in the Arctic. We'll talk more about that later. But one other thing that we wanted to look at is, what does this do to precipitation? And we found something pretty interesting in that the precipitation over the Sahel region of Africa, which is a drought-stricken region, is substantially increased due to these SO2 perturbations. All right, so you can see, especially in the upper panel here where my mouse is at the moment, that we're getting, significant increases in Sahel rainfall, which, could be viewed as something like a co-benefit almost. It's, a drought-stricken region. And it also sort of, I'm not showing this, but it lengthens the season of the rainfall. So like you have the monsoon season, it sort of lengthens that by a few days. So it really has a big effect. And one of the questions we wanted to ask was like, well, what's causing this? Because again, we're removing the SO2 over the US and it's causing the biggest precipitation changes in Africa. What's causing that? And so what it ends up being is this large interhemispheric temperature gradient that you see. All right, so in both of these models on the left, you see this huge warming in the northern hemisphere. What that does is creates an energy imbalance, which causes the northern flank of the Hadley cell to sort of go faster or go more extreme. And that causes sort of the ITCZ to shift a little bit and also sort of intensify. And that brings this enhanced rainfall right across the rain belt, basically, of the Sahel. So, just US SO2 emissions decrease, the northern hemisphere warms more with respect to the southern hemisphere, which causes this northward ITCZ shift and enhanced Sahel rainfall. So that was, some of you that are familiar with like IPCC and CMIP probably noticed that was an older generation of the models. That was using CMIP 5 era models, which, is 15 years old. No, more than that, probably to almost 20 years old at this point. We decided that we would start a study that looks at this with the new generation of this, and that's what's called the Regional Aerosol Model Intercomparison Project. The idea is broadly similar in that we're contrasting a scenario with slightly higher aerosol emissions compared to one with slightly lower, keeping everything else the same, and seeing what the resulting difference is in climate. One other improvement, though, is that you probably noticed that the simulations that I was talking about in the previous slides, those were very idealized, simulations. We're just saying, okay, what if you shut off all the SO2 somewhere, which is not necessarily representative. So what we did in this new set of experiments is we tied it to the SSPs. So the SSPs are these future projections of emissions. And it turns out that SSP 1-26 is a lower aerosol future. It's a slightly more clean energy focused future. And so you have lower emissions of SO2, black carbon, et cetera, compared to some of the other SSPs. Like, for example, in red here, we have SSP 370, which is more of a higher emissions. And so what we did is we just created sort of this hybrid scenario where we use the SSP 370 for everything except the aerosols, and we give it the SSP 1.26 aerosol. So we give it sort of has everything else, but has lower aerosols, and then compare that to the just the full SSP 370, which has the higher aerosols, and then everything else is the same. So you can sort of take that difference, and now you also have this time, transient nature of the experiments as well. So things are changing over time, whereas before we were just kind of cutting off the emissions and sort of setting it at that. So that's the nature of our experiments. We're doing these coupled simulations with 10 ensemble members per model. There's 10 models that are participating. It's very much a ongoing project. There's only a few publications out on it now, as we'll see. But really the idea here was to do, again, these regional perturbations, but sort of in a next generation way. So to get into some of the results here, this is the surface temperature response, the mean surface temperature response for averaging from 2025 to 2050. So the other thing is we're looking at sort of near term. We're not looking necessarily out to 2100. We're stopping at 2050 to look at sort of near term climate, which isn't that far away. And what I'm showing here again is the impact of the reduction of aerosols. So it's the lower aerosol case minus the high aerosol case. And this is the surface temperature. On the left, if basically the aerosols are reducing globally, so they're following the SSP 126 trend everywhere. The middle case is if they're just following the SSP 126 trend in East Asia. And then the far right case is if they're following it just in North America and Europe. So, you can see you get, not surprisingly, the strongest amount of warming over the Northern Hemisphere and over in the case where you have all the aerosols kind of simultaneously changing. But you still get some pretty significant changes over the East Asia and over the North American simulation. And one thing that's kind of interesting here is that the North American and Europe aerosol reductions are a lot smaller in magnitude than the East Asian aerosol reductions, right? And partially because North American and European aerosol emissions are already very far down at present day. And so there's not a lot further they can go. But the same couldn't necessarily be said about East Asia. So the magnitudes here are different, but the temperature responses are actually kind of similar in globally averaged nature. So the efficacy of these North America, Europe aerosols seems to be a bit stronger than over East Asia. The other thing that jumps out to me, at least, is that, again, there's a lot of Arctic warming. All right, so you can see it a lot in the global slide here on the left. But the Arctic delta T is about 3 times the global mean delta T. And so this is, sort of a classic case of Arctic amplification. We did a study that sort of tried to understand the mechanisms of that, and can refer you to that. But basically, the short answer is that we're expecting that there's more enhanced poleward moisture transport that's causing sort of enhanced moisture to the Arctic, which then has sort of a greenhouse effect and causes additional warming over the Arctic.
Dan?
Yeah.
I want to ask a question about
Sure.
the Arctic part of, what happens if you reduce SO2 or other aerosol precursors on Arctic temperature. To what extent do you have to know that it's meaningful? Do you have to get the impact of wildfire aerosol in the Arctic right? I mean, it's changed. The impact of wildfires on Arctic aerosol has really gone up in the last few decades. Do the models capture that, and how much does it matter?
I don't think the models capture it particularly well, to be honest. How much does it matter? I think I don't want to diminish it, but I think it probably, what we're finding is that the AOD changes are so much smaller over the Arctic as compared to, say, even the US, that the local effect is not necessarily thought to be as big of a driver of the change. Now, there's a few shortcomings in these models that could change that answer. And one of them is that they don't simulate, for the most part, some of these feedbacks, like the deposition of black carbon onto snow that then causes a melting feedback. So there's things that are missing in the models that could sort of change that a little bit. But from what we're seeing, at present, it's mostly that it's sort of these long range circulation change patterns that are driving the temperature change. Yeah. So I wanted to zoom in here a little bit on the East Asian simulation. All right, so this is the scenario where only the East Asian aerosols are lower in the future. And what we're getting here on these plots is the surface temperature change. So this is the time series, and the black line is sort of the mean here. So if you only reduce East Asian aerosols, you'd have a global increase of surface temperature up to about what is this, 0.1 degrees Celsius by 2050. It sort of increases over time. These plots here, these bars are the different models. So we used, I think there's 7 or 8 models here. Not all the models have finished all their simulations, so there's, we're not quite up to 10. And then down here is the surface spatial distribution. One on the left, I believe, is for boreal summer, JJA. On the right is DJF. So most of the Arctic amplification happens in the boreal winter. You can see these huge, increases of up to 0.5 degree Celsius. So this is pretty substantial, just for one region. And I forgot to also mention that this is for removing all types of aerosols together. So I'm no longer saying only SO2. This is if you remove SO2, BC, organic aerosol, everything all together. So there's going to be some competing sort of trade-offs there, because if you remove the BC is an absorbing species. It warms. If you remove it, you get surface cooling. So there could be, you know, some trade-offs here that are going to that, but still the overall is the removal of these aerosols causes a warming. And when we saw this result, we were thinking, wow, there sure has been a lot of aerosol reduction over East Asia in present day. So is this already happening to some extent? Could this explain some of the recent acceleration in global warming that we've had? And we think that the East Asian aerosol reductions over the last 15 years has likely contributed to this acceleration in global warming. So I move that there so you can see. So what you're seeing here, and this is sort of the evidence of this, the upper left panel is the global surface temperature anomaly from GISTEMP and HADCRU and NOAA and other things. And there's a couple, like one of them is the black line is sort of filtering for some variability. The gray dots are just the raw HADCRU or GISTEMP stuff. And you can see, you know, there's been some debate about this, but you can see that, you know, post 2010, there has been maybe a little bit of a acceleration. I mean, again, that's debatable. So, you know, maybe not the final answer on that, but this happens to correspond very well with the time period where aerosols in East Asia started coming down. So we thought about, could we use our simulations to address that? And that's pretty much what we did. We sort of took this trend that we got in the future simulations, which just happened to be about the same AOD decrease. So this AOD decrease that we're getting in these future scenarios were almost exactly in magnitude to like what has happened from 2010 to present day. That wasn't really by design. That sort of just happened in our experiments. So we could use that to sort of, you know, paste on this trend. And what we did is we took the ROMIP trend, which is the future, and added it to the 1980 to 2009 trend. So starting in 2010 here, this is what this this black, third time's a charm. The red line here is the ROMIP trend. And then again, the black and the gray are the observations of surface temperature. And you can see that the ROMIP simulations, you know, sort of do have some sort of, you know, bisection or some kind of, you know, overlap here of these, this increased, you know, acceleration, if you will, of recent warming over the last 15 years. So, you know, the take home there is that we do think that the aerosol cleanup has contributed to the acceleration of global warming in at least some extent. You know, there's other things that have contributed as well. A lot of people have pointed to the marine shipping emissions. There was a rule put into place that the sulfur content of international shipping fuel had to be a lot lower, and removing that sulfur, just like in what I was talking about earlier, increases your temperature, and so that probably had some role to it as well. But certainly the East Asian aerosol cleanup is part of the story. Okay, my last slide on the kind of climate stuff here. We also wanted to look at we also wanted to look at precipitation. And so I do a lot of work in Africa, as you're going to see in a minute. And we wanted to look at what the impacts on the Sahel would be, or on the West African monsoon. And so we did that. We did, again, with 8 models, we looked at the reductions in local aerosols. So this is or I shouldn't necessarily say reductions, changes in local aerosols over Africa. This is what you get in response to that, the precipitation. This is the changes in remote aerosols. So this is from North America and Europe. And then the final row here is the reduction globally all at the same time. And so one thing that pops out is similar to what I was saying earlier. You do get sort of this like ITCZ shift pattern especially in the North America, Europe perturbations, but even so to some extent in the Africa perturbations. And you get also that most models agree. There's especially UK ESM here on the far right. There's something different going on in that model, maybe a little bit in CAN ESM, the Canadian model. But largely overall, there's some agreement here. But if you sort of roughly add up what the impact is of the local aerosols plus the North American and Europe aerosols, it almost perfectly agrees with the global here. I haven't actually done that summation, but you can sort of eyeball it and see that, if you let's just take this column here, EC Earth, if you add up, these big changes, you kind of end up the sum of this third row down here. So the other scenarios were not really affecting precipitation in Africa too much.
What do the diagonal lines represent?
That's statistical significance in each model at the 95% confidence level. Yeah.
Thank you.
Okay, so I'm gonna skip now to the second part of this talk. And how am I doing?
So before you go
Sure.
to the second.
Yeah.
The question, the lowest scenario and the highest scenario is from the SSP, like 3 point something minus the low SSP pathway. is it?
Yeah, so it's SSP 37 minus SSP 126.
Okay.
Yeah, so, yeah. We're gonna shift gears now and talk about air quality more. And probably goes without saying, but exposure to air pollution is the second leading risk factor for premature death for all causes, not just for environmental causes. So it's second to high blood pressure. And a lot of these deaths happen, in developing economies, global South and Africa, South Asia as well, a little bit, which is what these plots here are showing. This is just a sort of kind of personal representation of this. So these are some filters that we collected particles on in July in Nairobi, Kenya. After a few weeks, the left here is what we got versus a clean filter. So you can just imagine, sort of breathing that into your lungs wouldn't be good. Within Africa, there could be about 1 million premature deaths per year due to PM 2.5, although it's a little bit uncertain. One thing for sure, though, is that there's not a lot of data to make these estimates very good. All right, so in order to be able to say how many folks are dying prematurely due to poor air quality exposure, you need the health data, but you also need the exposure data. And this plot is showing the density of PM 2.5 monitoring stations per million people as of 2022. So the red is less than one monitor per million people. The gray is zero. There's no monitoring. So a lot of the countries in Africa, it's completely, there's no monitoring. Some of them, it's, there might be like one monitor in the whole country. And then, contrast that with the US, where we have, plenty of air quality monitoring. So we can't really, fully solve this problem if we don't know what we're dealing with. And so a lot of what I've been focusing on in this area is sort of closing that air pollution data gap and figuring out, what kind of levels we're seeing, what are the characteristics of the aerosol, what are its chemical compositions, what are the sources of the aerosol. Those are the things that we'll talk about here over the next few minutes. And if this goes unaddressed, we could see that mortality, projected mortality in Africa by 2050 could increase by quite a bit. It could be, 2 times the present day levels. And
Could I just ask, what's the definition of a premature death? Like 5 years, 10 years, or 1 year?
I believe it's anything that is below sort of the average lifespan. I don't think there is a specific number, like 1 to 5 to 10 years, but yeah, I think that's more a question for the epidemiologists. So I'm not 100% sure. Okay, so so I was mentioning that the premature mortality could get worse. This is a busy plot that we don't need to focus on too much, but basically we did another modeling study where we looked at what is the present day premature mortality in different parts of Africa, and then what could it be by 2050, depending on a few different scenarios, a few different emission scenarios. And the answer is basically, at present day, at least in this model, it's maybe about 1 million, or actually slightly less than 1 million, and it could reach, close to double that by the end of 2050. All of these first few columns here are present day or close, or I guess you say recent past, close to present days, 2015, 2016, 2018. And then after that, you start getting into the 2050. And each of these different 2050s are just different emission scenarios. Don't worry too much about what they all are. I don't really have time to go over that. But most of them give you a similar story, is that the levels of excess deaths go up quite a bit in the future. So yeah, there's higher emission scenarios, lower emission scenario here in green. This is SSP 119. So this is even lower, cleaner future for climate and pollution. And so you get slightly lower, but it still actually does increase. The deaths still increase from present day. And part of that is the population is changing. So Africa is the fastest growing continent. So there's more people, and the population could double by the end of I think it's projected to double by the end of the century. So maybe not by 2050, but needless to say, a very fast growing population. So we've been looking at, sort of motivated by that, what are some ways that we can address this and get more data? And so we've been working in a lot of cities to, in some cases, get the first distributed or large networks of air quality measurements. And this one I'm showing here is based in Ghana. So this is in Accra, Ghana. It's the largest city in Ghana. The map you're looking at on the right is showing you the locations in the city that we measured. So we had, I think, not all of them are pictured, but we had about 18 sites. This was the first air quality data pretty much at all in this city. And you can see that there's these pies. There's these, maybe it's hard to see, but there's these red and yellow pies and a number by it. And those numbers and the pies are representing the percentage of days in a year that exceed the World Health Organization healthy guidelines for PM 2.5. And so basically the numbers are all very high. It's almost every day is the take home point. This is a sort of distribution of the daily averages on the left here of PM 2.5, and then the dashed line is the healthy guideline. Actually, it's the recent one that the World Health Organization lowered their recommendation even further to try to get cleaner air, or force policymakers to go for cleaner air. So it's lower than this now, but the point remains is that most of these daily means in these distributions are well above the healthy levels. So this is one way to get at this data, but there's you can put measurements all over. It's going to be hard to cover everywhere. I mean, resources are limited. We have a good monitoring network in the US, but even it has some gaps and some lacking in places. So one thing that we've thought about is, what if we turn to remote sensing? Because remote sensing has, almost a perfect, quote unquote, spatial coverage, in that the polar orbiting satellites especially are, seeing every part of the Earth once a day. The geostationary ones are seeing a certain part of the Earth many, many times a day, and that's kind of a different story. But we used the MODIS basically is sort of the workhorse of this methodology. But we used MODIS, and we developed a machine learning model that is trained on our network of ground-based data throughout Ghana. And we were able to sort of fuse the two together to develop this gridded high spatio-temporal resolution data set for PM 2.5. And so you're seeing a map on the right for some particular day of what that looks like. And I don't have time to go into this, but it does agree very well with data that it wasn't trained on. So if you compare this derived satellite machine learning PM 2.5 data set with independent surface observations, you get high R-squared, low bias. So it seems to work pretty well. And all the data is online on our group website if you're curious. So This is another way. With the other thing with satellites is they have a long temporal range. All right, so MODIS started flying in, I don't know, 1999, 2000, 2001, something like that. So in theory, we can go back all the way to that. And if you need to do epidemiological studies, or if you want to do policy evaluation, a lot of times you need long-term data. You know, you can't just rely on data that you started collecting 6 months ago. That's not super helpful. So that's another really important application of this methodology. I'm not going to go into all of these, but we've done this in a lot of different cities in Africa. They're pictured here on the left in this map. These are the places where we've done some kind of like similar study with sensors and remote sensing. But one thing that would be nice is can we get better information out of this? You know, just having the concentrations and saying they're high, they're exceeding levels, that's great, but it's not as actionable. And you could probably just visit the places and breathe there for a day and be like, yeah, okay, concentrations are high. So can we attribute sources? Can we figure out what's going on? And so we piloted this methodology in a city called Kinshasa in the Democratic Republic of Congo. It's actually, this population is probably somewhere around 18 million. It's quite large. And we collected a series of gaseous and particle data using sensors. All right, so these are basically low-cost sensors. We evaluated them against you know, lab methods, research grade methods, stuff like that, to make sure that they were pretty accurate. And we found high levels, not surprisingly. But what we wanted to do is sort of, can we use this data to attribute sources? And we're going to use a non-negative matrix factorization approach for that, similar to positive matrix factorization, which I'll talk about at the end. But basically, we take that time series of PM and gases and factorize it into a combination of matrices that gives us one of the matrices that it gives you is this sort of contribution of each species to a given factor. So these factors that it gets are hopefully physically interpretable based on that contribution matrix. And you could say that, okay, factor 1 could be cooking emissions or something like that. So this is a not uncommon way of doing source apportionment in the field of atmospheric chemistry. So we did this for Kinshasa. We collected data for 6 months. We collected size distribution data. So we had an optical particle counter that was giving us size bins throughout the range of aerosols, and then also a series of gases. And we looked at things like the factor composition, which is shown here on the upper left. So you have, like, for example, one factor that's dominated by CO. This brown bar here is CO. You have another factor that's dominated by smaller sized particles. So this blue here is bin 0. So these are like 300 nanometer particles. These are relatively small. Then you have another factor that's dominated by NOx. All right, so this orange bar here is NOx. And so you can kind of take that information and combine it with other sources of information like the diurnal profiles and also with the wind speed and wind direction and sort of tease out what the sources of pollution could be. And so we've done that. We found factor 1 was probably local combustion from vehicles and cooking. Factor 2 most likely to be combustion from primary sources, so small fires. And then factor 3 had a unique diurnal profile. It also had a big contribution from secondary species, ozone in particular. So this one is more likely to be regional in nature from like biomass burning in the inner parts of the continent where there's a lot of rainforest. Wind speed data is the other way that we can corroborate some of that information that I was saying. Wind speed, wind direction, it can tell you kind of where the data, where the factors are coming from, where they're the strongest. And the real strength of this is it's a really low cost approach for source attribution. So this piece of equipment that collects all this data, including the MET station, runs about $6,000 or something like that. The traditional way of source apportionment, collect filters, take them back to the lab, do XRF, do ECOC, do metals, do everything. It's a big burden. You could also have real time. You could have an aerosol mass spectrometer or something like that. Also very expensive. So we think that this could be especially promising in resource limited environments like Africa, where there may not be the feasibility to get 20 aerosol mass spectrometers all across the continent, like there is in the US, for example. So then the last bit, almost finishing up here, is I want to talk about moving beyond these sensors. And because sensors are great, they can give you some basic information, but it is important to understand a little bit more than that. And so we spun up a field campaign, an aerosol chemical composition field campaign in East Africa, in Nairobi. So we're calling it NBO Chem, the Nairobi Aerosol Chemistry and Aerosol Monitoring Campaign, a new field intensive that literally is just started earlier this year and is still ongoing. This is our site. It's in the urban core of Nairobi. So it's located at the Kenyatta University campus in Nairobi. It's pretty much, straight in the urban area. I mean, you have like the president's house only a few blocks away. You have major highways and bus stops only a few blocks away. You have the financial center of the country, right nearby. So it's really much in the heart of everything. The campaign began in February. We still have some equipment there, but the aerosol mass spectrometer part ended in September. This is the equipment. So I guess the flagship piece of equipment is the Aerodyne TOF ACSM. It's an aerosol chemical speciation monitor. It's a mass spectrometer basically that can give you the organic composition, the nitrate composition, the sulfate contribution, ammonium chloride, and then it can give you sort of the resolution of individual molecular fragments, individual species, so that you can really pinpoint sources in a lot better way than the low-cost methods that I was talking about earlier. We also have a black carbon monitor, an ozone monitor, a NOx monitor, and then I'm not going to talk too much about that data. We're going to focus just on the aerosol here, but we also have a aerosol scanning mobility particle sizer that can give you the size distribution. So if we just look at the data in time series here, this is what we get. So the left panel, the left axis, the left y-axis is the organic concentration, and the right axis is the other species. This is partially because the organics were way more elevated than the other species. But we had sort of, one period, there was actually 3 periods of high quality data. But I'm only showing period 2 and period 3 here. So period 2 is the wet season, rainy, and period 3 is the dry season, but also the colder of the dry seasons. And this sort of summarizes the chemical composition. So the short answer is that aerosol is mostly organic and mostly black carbon. I guess you could just say mostly carbonaceous to keep it simple. Campaign period 2, which was a little shorter, we had 84% organics. If we include black carbon in that, for campaign period 3, we had a little bit lower. This is the colder period, so we had lower, probably less. In the colder period, we had slightly less organic concentration. But if we add in black carbon to this, black carbon takes up a pretty big chunk as well. So, 37% of the PM mass was black carbon if you include that. And then that brings the organic down to about 50 in total. Well, one thing I wanted to mention also is that these concentrations are quite high. So this is what the ACSM is actually measuring is PM1, not PM2.5. But, we're reaching upwards of 50 micrograms per meter cubed just from the organic. You're reaching something similar for the BC. I think the BC is like in the range of 20 to 30. And then all these inorganic species are closer to, 5 to 10. But so add all that up, you're talking about extremely high levels of aerosol pollution. And then what we can do with this data, what's commonly done is something very similar to the non-negative matrix factorization I was talking about. This is the positive matrix factorization. And what it does is it distinguishes between different sources based on the mass spectra. And then the mass spectra can also give you different classes of organic molecules. So you can say something is more likely to be hydrocarbon-like organic aerosol, HOA. Something is more likely to be oxygenated, or sorry, oxygenated organic aerosol, OOA. BBOA, biomass burning organic aerosol, cooking organic aerosol, depending on like which mass to charge points in the mass spectra are higher or lower, you can find out, basically, determine what these sources are. So it's a really good source. It's a really good method for real-time source apportionment. If we look at our data, this is just from that longer period in the dry season. We came up with 5 distinct factors. So this is the spectra, mass to charge ratio on the x-axis, and then the signal on the y-axis. We came up with a handful of different factors here. A hydrocarbon-like organic aerosol. So this is the source here would be buses, traffic, vehicles, cooking organic aerosol, but cooking specifically from the fuels. So it's really like LPG emissions, kerosene, possibly a little bit of like charcoal as well that's used for cooking. The different peaks here kind of tell you like whether or not a certain type is that cooking. Biomass organic aerosol, another cooking factor which is more likely to be from the oil and the food, so not necessarily the fuel. And then oxygenated organic aerosol, which is could be regional biogenic from, there's a lot of vegetation in the area. It could also be emissions earlier in the day from anthropogenic sources that were not oxidized, that evaporated and that later were oxidized back into SOA. The other way that you can help sort of tell this is by looking at the diurnal cycle. So just as I was doing with the non-negative matrix factorization, the diurnal profile gives you some hints as well. In particular, down here on the bottom right for the OOA, the oxygenated organic aerosol, you can see that it peaks as the sun is up. From about 6 a.m. to 6 p.m. is when OOA is happening, and that's because it's photochemistry. All right, so you need OH, you need oxidation of VOCs and things. So just to summarize this part, we found that about 22% of the PM is from traffic emissions. Roughly 30% was from cooking, and all inclusive. So, LPG, kerosene, charcoal, but also meat and oil that's used for cooking. Around 13%13% burning. So this would be the biomass burning. This could be wildfires, but also like small brush fires. And then roughly 36% from aged regional biogenics, in the surrounding vegetation area. So I will just stop here. I'll leave up my summary and take-home points I'll come back to them and have you guys just look at them since we're running short on time, I think. But I just wanted to just thank all of my funders for this work and thank my group, and I'm happy to take any questions. Thanks.
All right, thank you so much, Dan. I think we have time for 1 or 2 quick questions, and then we can move the rest to the lunch. Yes, please.
So, you found the Nairobi multiple times last year. You go down to the central business district. The congestion is so overwhelming, traffic congestion, those buses, isn't that the dominant in the central business district?
It was certainly one of the higher factors, I would say. But I don't think it's necessarily the only one. And you're right. There's definitely a lot of traffic. There's a lot of bus or matatus, as they call them, sort of like informal mini buses. It could be that just our location is not necessarily like super close. I mean, we're about 300 meters from the main Nairobi Expressway, and so it could be that we're just off a little bit from that, and that we're getting, more influence from cooking, which is one of the major factors. But yeah, I mean, I think traffic is one of the most important ones. But our analysis so far, which again is a little bit incomplete, it only is a few months of data, shows that it may not be the primary source. Yeah.
Yeah. take
I,
last-
I have a friend in Boston, his name's Eric Worcester, who spent quite a bit of time in Kenya. His wife's a doctor there, but he developed a efficient, little, very efficient wood burning stove for women in very simple rural conditions that creates a lot less smoke, and these little shacks, don't have proper ventilation. And it's now an African country, and there seems to be very effective.
Yeah.
And he's actually marketing this in the US as well for hikers.
Yeah, I mean, that's one of the solutions. There's a lot of good solutions oriented people that are working on uptake of those kind of stoves, but also LPG. So LPG is still a fossil fuel, but it burns a lot cleaner in terms of air quality and climate. And there's been a lot of studies that show that if you're choosing between just burning wood or charcoal, which is the easiest way to do it, because if you can go out and just chop down a tree for free, basically, and use that to cook, costs nothing. But so there has to be some kind of like economic incentive for people to use these like more advanced things.
Well, obviously, that's in rural areas where say LPG would not be available,
Yeah,
not the cities.
right. In the cities, people tend to use charcoal mostly. The LPG take up is trying to break through, but again, it's more expensive. So in other countries, they've had a lot of, like India, for example, has had a really high uptake of LPG, and I think they've, made some good strides on that. But certainly those are options.
So interior pollution and cooking and is really out of reach of your instrumentation.
Not really, because most dwellings in Africa are very well ventilated. So that the barrier between indoors and outdoors is kind of very slight in some cases. Like schools, for example, when people are making the lunches for the kids, they're doing that in like a room that has a roof but completely open to the sides, so the pollution can get out.
Awesome, thank you. We can take more question and conversation to the line. Awesome, thanks. Yeah, no problem. Yeah.